Thanks, Adam. I'm going to talk about this, for instance. So what is the problem here? So here you see the adjacency matrix of a graph. So the blue things are the non-zero entries, and the white things is edges which do not exist. So it's a sparse graph. And so these are the same graphs. The only thing I've done is, so here I took this graph from a matrix collection. It has 161 nodes. It has a certain number of non-zeros. And so this is how you find the graph in this collection, or the matrix. And here I tried to somehow simultaneously change the rows and columns of the matrix in such a way that the non-zeros get packed as much as possible to the main diagonal. So here the bandwidth, you see this little blue dot is close to column 80, so the bandwidth is 79 in this graph, and here everything is much closer to the main diagonal. Yeah, okay, thanks. If you don't listen, then I will use it. So of course, so the bandwidth problem is important. So it's so suppose this matrix is the system matrix of a linear equation. So a symmetric positive definite system, and so if you want to solve this system, for instance, using the Cholesky decomposition, so here I gave some timings in MATLAB. So I took one of the matrices from this collection. So this matrix is of order 5,000. 5,000 by 5,000, well, 5,300. It has about 100,000 non-zeros, so it's a real sparse matrix. Now, if you take this matrix as it is, so every zero entry is zero, so you take it as a full matrix, you compute the Cholesky factor. It takes 7 seconds on this computer, which is fast, but and you can do much better if you first of all, if I store it in sparse format. So if I tell the computer that zeros are zeros, so that you don't have to do anything with it, you get a speed of about 10. It takes only 0.5 seconds. If on top of it, I try to reorder the matrix in such a way that the bandwidth after reordering is small, then it takes only 0.07 seconds to find the Cholesky factor. So all in all, it's the same matrix. I haven't done anything substantial, but it's a speed of 100. So it's worth to have small bandwidth. Now, another thing in the title, so maybe I should go back to the title. So I will talk about bandwidth and separator problems, and I'm interested in actually finding good reordering so that the bandwidth is small, or finding good reordering so that I find vertex separators of small size. And I want to use optimization techniques to get to those results. And I should mention this is joint work with 2 people from Paris, Abdel Lissa and Juan Xu, I think that's how you pronounce it, and Mauro Piacentini from Rome. Xu. Yeah. Yes. So this was the bandwidth. Small bandwidth is useful. Now here's the vertex separator thing. So suppose I give you the adjacency matrix of a linear system, and the linear system, the adjacency matrix looks like this. Now if you want to solve a linear equation with this system, it looks somehow interesting to say, okay, let's just throw away the last few equations and the last few variables. If we would do that, we would have 4 small independent linear systems, and of course using just standard mathematics. So here I gave an example with 2 blocks. So if the system matrix would have this structure, so A1 is a big block, A2 is a big block, they have nothing in common, and then there's a small tiny block A3, so maybe just a few variables, then you could say this system could be solved essentially by solving the system here on X3, a small system of size order of A3, and then you do just some back substitution. So using Schur complement arguments. So the point is, if I would have this structure, if I have, instead of order n cubed operations, I would have an effort of order n cubed divided by k squared if k is the number of blocks. So this is interesting. But of course, the question is, if I would permute the rows and columns of this matrix, you would not see anything. It would be just a blue picture. There would be blue spots all over the place. So the question is, given possibly unstructured patterns of non-zeros, how can you detect whether such a substructure exists after reordering the nodes and columns? This is what I would like to talk about. Now, in computer science, you often do the following. You say, suppose I want to find 2 to the k blocks. You could go recursively. So you say, okay, the first step, I try to find a separator having 2 big blocks. Then I take each of the 2 blocks and separate them again, and keep going. Now, of course, if you made the wrong decision on top, you will have a mess later on when you want to recurse. So it would be more interesting to say, well, just find the 2 to the k subsets directly. Give me a separator such that the graph disconnects into k components of roughly equal size. So this is what I'm interested in. Okay. So the problems are difficult. So both problems are NP hard, and bandwidth, for instance, is even NP complete if you look at trees, and the largest degree in the tree largest vertex degree is 3. So these are very simple graphs, basically. There are some approximation results for the bandwidth problem. There are approximation results for the vertex separators. So here you see some names. Of course, there's an very old result by Tarjan, Lipton and Tarjan from the late 70s that actually show that you can always find a vertex separator in a planar graph on n nodes, and the size of the vertex separator is order square root of n. But of course, it doesn't say that this is the smallest separator. So it could be that the smallest separator has size log n. And I've looked at this problem in the context of eigenvalue optimization jointly with Christoph Hellenberg and Bojan Moha and Svata Poljak long time ago. So, and more recently also with Janez Pof in the context of semi-definite and co-positive models. And basically, I'd like to show you now how we can use these 2 approaches to come to something which is practical for big problems. So we will not be able to use semi-definite programming. If you want to attack practical problems, so problems say a linear system of order 100,000 comes from a discretization of a differential equation, you're not going to use semi-definite programming.
Can I ask a question?
Yes.
So in terms of the practical applications, finding this good permutation could take longer than solving a linear system from scratch. So presumably you only use it if you're going to solve the same kind of linear system over and over again. Does that make sense?
For instance, yes. So typically, often what happens is you have your discretization, and then small things change, so you solve the same system, but the parameters change.
Yeah.
And so it's worth to spend some limited time. So you're right, you don't want to spend more time finding a reordering it takes to solve the underlying problem. And also, from a practical point of view, you really don't care whether you reduce the bandwidth to, say, 100 or 110. I mean, and if the separator, yes?
So I want to ask, are your matrices sparse?
Yes, of course. So it only makes sense if the structure that you give me is extremely sparse.
So then edge separators would be roughly the same as vertex separators?
Yes, I come to this. Yes.
So am I correct that sparse methods for finding a Cholesky factorization actually incorporate some kind of preprocessor to make things sort of sparser.
So if you look at the sparse matrix and you want to know where are the potential places for non-zeros in the Cholesky factor, this is completely understood. So the fill, it's called the fill-in in the Cholesky decomposition. So the fill-in is completely understood, and basically fill-in is small, roughly speaking, if the bandwidth of the representation is very small. This is basically what it comes down to. Not exactly, but roughly.
You're saying that I understand that practical implementations actually incorporate this preprocessing, some kind of heuristics to find the reorderings.
Yes, so if I would solve a sparse linear system of, say, 50,000 variables, I would be willing to spend some time to reorder the coefficient matrix to speed up the computations. So there are all kinds of matrix reordering problems. So minimize bandwidth, minimize Cholesky fill-in. So this one sum, two sum. This is different ways to measure the distance from the main diagonal and yeah. So even MATLAB. So those that use MATLAB, this command here, sim-RCM, the symmetric reverse Cathil-McKee algorithm, is actually quite a useful thing to use. So it's a heuristic, but it often finds very good orderings. And here are some other MATLAB commands. Okay, so here's how I want to model the problem. It's going to be indirect, and here's the basic idea. I look at the following auxiliary problem. So I allow to partition the graph into 3 pieces, S1, S2, S3, and the sizes, and I specify the sizes. So S1 has size M1, S2 has size M2, and S3, so the last bit is going to be the separator. So S3 should have size M3, and the idea is that M3 should be small. Okay, so now what is the auxiliary problem? So I would like to consider all possible partitions into 3 sets of the given cardinalities, and I would like to do it in such a way that the number of edges joining S1 and S2 is minimized. I call this the min-cut problem. And I denote the optimum by cut of M, because it's specified by the cardinalities in this vector M. Now suppose I can compute cut, this min-cut optimally. Then I argue if for a given configuration of the cardinalities, M1, M2, M3, if I can show that the best possible partitioning still has edges between M1 and M2, then I argue the bandwidth of the graph must be at least as large as the set here in the middle plus 1. And the reason is the following. I take the optimal ordering for the bandwidth, and I say, okay, the first M1 nodes, the first M1 elements in this ordering go into a set S1. The last M2 elements in this ordering go into the set M2, and then I know, since there are edges between S1 and S2, they have to jump over the remaining piece. So in other words, the distance is at least M3 plus 1. And on the other hand, of course, this is more obvious if the cut is 0. So if I can find a configuration where none of the edges is cut, then I immediately have a separator. That's clear. And so we are going to use so of course, this problem finding cut M, so finding the best possible solution, is difficult. So the idea now is that we are going to use a relaxation, so a lower bound. And if the lower bound is positive, then of course I know that the original value is positive, and I can conclude something about the bandwidth. And otherwise, I can conclude something about the size of the separator. So, okay, let's model this mathematically. So, I do this in the following way. So before I looked at the case where I only partition into 3 blocks. Now I take a more general viewpoint and partition into k blocks, because I'm going to use this if I want to find separators of large, if I want to find a separator that produces k minus 1 blocks, that disconnects the graph into k minus 1 sets. So originally I had k equal 3, so I had 2 sets in which the graph decomposes. So
the goal is to minimize the number of edges between the first k minus 1.
exactly, yes. Because so I'm going to massage this edge set into a vertex separator by just increasing the size of the vertex separator. So here I have, for instance, 5 blocks. I have these 4 blocks, and this little block here would be the separator. So I go for general k. And so I do the natural thing. So I introduce an n by k matrix of zeros and ones, and each column of this matrix tells me which node goes into the respective set. So what obvious properties are, well, so E is the all ones vector. So if I look at the row sums of such a matrix, then it's clear that well, if this matrix X has some zeros, so this is the set 2, and this is set 3, and so on, then it's clear each vertex must be in exactly one set, so the row sums are 1. And if I look at the column sums, so this is X transpose times the vector of all ones, well, the column sums must be exactly the cardinalities that I want to see. And X is 0, 1. Now, so the 0, 1 condition is not really something that we can work with. So I'd like to have a different description. And actually it turns out, if you would maintain the linear equations, so row sums equal 1, column sums equal m, and if you throw away X is 0, 1 and replace it by X transpose X is the diagonal matrix M, which has the m i's on the main diagonal, and if you would ask that X is non-negative, this would be an exact description of this set. So I leave out non-negativity of X, so I get a relaxation, and now this set is I can work with. So what is it? We have a bunch of equations, and we ask that basically that the columns of X, the columns of this matrix here must be orthogonal. Okay, but first we have to model the cost function. I think this should be the next slide. No. Okay, we skip this slide, I come back to it.
Sorry, another question. Is that last constraint non-convex then? XX transpose equals?
Yes, absolutely.
Okay.
This is you're somewhere on a sphere, but only parts of a sphere.
So you are going to replace it by something easier, right?
No, I maintain orthogonality.
Okay.
Yes. So how can I model? So here is the matrix X again in the n by 3 case, and let's introduce this matrix, this 3 by 3 matrix. Basically, in the k by k case, I would have ones for all the blocks where I count the partitions. So then it's clear that X bx transpose would be simply the complete bipartite graph joining S1 and S2. So in other words, if I take the inner product of this matrix here with the adjacency matrix, I get exactly the number of edges in the cut. Yes, that's what I say here. So X bx transpose would be the complete bipartite graph given by the bipartition S1 and S2. S3 is ignored. And if I take the trace inner product with the adjacency matrix, then I get twice the number of the edges. And now I don't like the adjacency matrix here. I want to introduce the Laplace matrix of the graph, and I can do it because the main diagonal of this matrix is 0, and the Laplace matrix outside the main diagonal is just minus the adjacency matrix. So I can write this function as that. Okay, so now the idea would be, so this is what we want to minimize this quadratic function.
So B is now fixed, right? But
B is fixed. B is so depending on the decision how many blocks I want to have. So B is either B is basically k by k.
Okay.
So 3 by 3, 4 by 4, whatever you want, and L is the Laplace matrix of the graph. And so now I want to. So this is quadratic in X. And so now what I would like to do is I would like to substitute. I would like to somehow use this information to solve this optimization problem. And the interesting thing is I can actually, so I skip this and here it is again. So I can argue that a matrix in this set here, so it means it satisfies equations of the type, so the row sums are 1, the column sums are m, so the cardinalities, and orthogonality so any such x can be written in the following form. Well, if I just look at the linear equation, so this is, I can say the general solution of a linear equation is one specific solution of the inhomogeneous equation plus the general solution of the homogeneous equation. And this is what's stated here. So 1 over m e times m transpose. Well, this is a specific solution of the inhomogeneous equation. So this matrix basically has 1 over n, and the first column is always m1. The second column is always m2, and so on. And if you sum up the columns, then you get exactly the cardinalities mi, and if you sum up the rows, you get 1. And this here is this thing here is the general solution of the homogeneous equation. So it looks awful, but it's really just trivial. So V is the orthogonal complement to the all ones vector. So a basis to the orthogonal complement of the all ones vector. So if I would multiply from the left with E transpose, so E transpose X is clearly on this term here would get 0 because V is orthogonal to E, and W is. So here you need some notation. So m tilde is the vector of square roots of the mi's. So you just need them to scale. And m tilde is the diagonal matrix. And this W here is an orthogonal basis to m tilde. So if you multiply on the right hand side with E, so a diagonal matrix times the vector of all ones gives me simply the main diagonal back. So m tilde times all ones vector gives me little m tilde, and little m tilde is orthogonal to W. So and this is why it looks complicated, but this is simply the general solution of the homogeneous equation. And the interesting thing is the columns of X being orthogonal is equivalent to saying that the columns of Z, so this matrix Z in there is n minus 1 by k minus 1, and the columns are now orthonormal. So basically what I'm going to do now is I use this explicit formula for X and substitute it in here. Okay? Of course, the X consists of the inhomogeneous constant part plus the general solution of the homogeneous equation. And because the Laplacian has the property that the rows, so the vector of all ones is an eigenvector to the 0 eigenvalue. So basically, the inhomogeneous part cancels out if it multiplies with the Laplacian. So what's left is, let's see whether, yes. So this is what I said. We substitute this, and so this is what we have, and this is what we get after substitution. And this looks complicated. I mean, this is an awful expression, but it's just basic matrix multiplication. It's a k minus 1 by k minus 1 matrix. So if k is equal 3, this is a 2 by 2 matrix which I can compute. Okay, so now the interesting thing is if you have such functions, so the trace of a quadratic function over orthogonal columns, this problem is an old problem and it has an explicit solution. So this can be traced back to John von Neumann. So I've just summarized. So this was the original problem. We go to a relaxation, we substitute, so we go from X, we go to Z. Z is now a matrix containing orthonormal columns, and we have, so these parentheses here, they are just complicated, they're just matrices, symmetric matrices, and there's an explicit solution to this problem. It's called, in some people call it the Hoffmann-Wieland theorem, but it can be traced back to John von Neumann. And it says the following: if you minimize such a quadratic form here, so A is symmetric n by n, B is symmetric k by k, X is k orthonormal columns. If you minimize this, then the minimum is this expression here. So you look at all the eigenvalues of the smaller matrix and you map them injectively to the eigenvalues of the larger matrix, and you do it in such a way that this injection is, that this term is minimized.
So for fixed k, this can be done in polynomial time.
Oh yes. This is you just compute the factorization of A, you can compute the factorization of B, and you determine this number here. So actually it's sorting. Yes, you sort. So.
Well, I mean, you can have. So you are just saying that actually k.
I don't care about
Yeah.
k.
What?
Yeah, k can be large, and you can still solve.
Yes. So the original theorem is by John von Neumann.
Maybe it's
starts
some
with
what kind of injections you are allowing, because in general you can have a lots of them.
Okay, so here's the original statement. So if A and B are n by n, so then the injection is a bijection. So you ask, what is the smallest possible scalar product of the eigenvalues of A and B if you're allowed to rearrange the eigenvalues? And it turns out if you want to minimize, you get the optimal if you sort one set of values increasingly and the other one decreasingly. Okay, so now this is k by k. So I could just pack this k by k matrix into an n by n matrix by just adding zeros. So it means I would add the right number of zeros here to the matrix B, and then I could sort. So the injection is not an issue, the optimal injection. See what comes next. I don't know. Oh yes. So what I'm saying now is we have this matrix here, so this projected matrix. So just because we substituted. So this substitution here, we have to compute all the eigenvalues here, and we have to compute all the eigenvalues here. That's what I'm saying on the next slide. And it turns out that the eigenvalues of this k minus 1 by k minus 1 matrix has the property that all are negative except one which is positive. So I know which ones are negative, and I know the remaining one is positive. So the sorting says take the most negative one and multiply it. Yeah, and the eigenvalues of this matrix of V transpose LV.
So it allows you to find the minimum, right?
Yes.
But can you recover that matrix X?
Yes, I think it even was on the slide. Maybe I was. Oh yeah, here. So I have the minimum,
okay.
and then you just take the corresponding eigenvectors. So in the right order. So in P I have the eigenvalues of of the phi i's of A, and in Q transpose I have the eigenvectors of B in the right order, and this shows that this is the optimizer. And in fact, if the sizes are all equal, so if the first k sizes are equal to S and the last size is T, then you can write down explicitly what the eigenvectors of this k minus 1 by k minus 1 matrix are, but this is not so important. Okay. So what do we know? Up to now we have the following situation. We have a problem where we approximate this cut of M from below, and we even can find an explicit optimal solution to this relaxation. So the resulting matrix X is okay, except that it may have negative entries. So the only thing that we did not include is sign constraints on X. And so now you could say, well, this Hoffmann-Wieland theorem here, and I will come back to this. This is actually, this can also be formulated as a semi-definite program. This here is a semi-definite program. So you could say, okay, let's add the power of semi-definite programming and make the relaxation tighter. This is not what I want to do, because I have in mind that the problems that I would like to solve, they are too big. So if you want to reorder a matrix of, say, of 50,000 nodes, maybe semi-definite program is not the first method that you would like to use. Okay, so I have another idea now, and this is what I've been. So this is the new stuff. So up to now, this was already we've already looked at. So the new idea is the following. So this quadratic program gives me a lower bound on the cut value, on this cut of M. So the number of edges in between S1 and S2. And I'm really interested to know whether this cut value is 0 or positive. If it's 0, I have something about the vertex separator. If it's positive, I know that the bandwidth is at least, I have a lower bound on the bandwidth. So I can do the following. Suppose, so now I consider the adjacency matrix as a weighted graph, and I say that each edge weight is 1. So the non-zeros of the matrix have weight 1, and so the total weight is the sum of the edges. So now I could say, suppose I allow to vary the edge weight. So instead of 1, maybe one edge gets weight 1.5, and maybe another edge gets weight, say, 0.3. And so what I'm doing now is I try to vary the edge weights in such a way to get the bound better. So if my current lower bound is negative, so if this eigenvalue term here, if this thing here is negative, I know nothing, because the cut is at least 0, and so if I could by redistributing the weight on the edges, if I could make the lower bound from negative to positive, I would have gained information. And this is what I would like to do. So
this rebaiting of the edges, in some sense, that's what the SDP would do in the dual.
yes,
And so in some sense,
if you ask the SDP to do it.
if you do it optimally. So,
Yes.
so I guess, you could
Have you
say
seen
that
the talk before?
No, but these things. But even Williamson, if you look at the dual,
Yes.
it rebates the vertices.
Yes.
And, so I guess you would say that you're sort of solving the SDP by iterating some kind of eigenvalue approach.
Exactly.
Reweighting.
Exactly. That's the plan that I'd like to follow. So what do we need to compute this lower bound? So we have the Laplacian, and we need the largest Laplacian eigenvalue, lambda n. And if you partition into k blocks, we need the second smallest, and the k minus 1 smallest, up to the k minus 1 smallest. So if k is equal to 3, we are happy with lambda n and lambda 2. And so now, so computing extreme eigenvalues of a symmetric matrix, if the matrix is sparse, this is something that can be done computationally efficient. So you don't have to compute all the eigenvalues, they are iterative methods. And you know about this, because this is what you are using as well, I suppose. Okay, so now we use this weight redistribution idea, and this has been employed by other people as well. So this is not my idea. So when I was reading these papers, I thought this is something I should try out myself. And so Boyd, Diaconis, and Zhao in 2004, and also Christoph Hellenberg with his people in 2008 looked at this problem. So weight redistribution. So this is what I said before. So L is the Laplacian, and now I take a more general family of graphs. So I stick to the support, and now I allow on each edge a weight xij. So this is now the Laplacian depending on the edge weights. So actually xij is, it should be greater or equal to 0. So I definitely do not want negative edge weights, but if they want to go to 0, that's okay. And the sum of the edges should be the number of the cardinality of number of edges in the original graph. Okay, so now the question is this lower. So this is the lower bound, as I have written it before. But now it's a function. It's a function of the edge weights. So basically, you could think of this. I have a matrix which linearly depends on some parameters x, and I look at the eigenvalues of this matrix. So these are matrix functions, and I want to maximize this expression. And it turns out that this is actually concave. So lambda max is a convex function. So here we have minus lambda max, so it's concave. So we're on the safe side. So maximizing this problem is a concave problem. So it's okay, we can do it, it should be tractable. And in fact, it actually is a semi-definite program. So maximizing this function is a semi-definite program. Why? Here's the answer. So I come back to the original statement that minimizing this quadratic form over orthogonal matrices. So here I just take A and B to be n by n matrices. So this problem here is the same as this, the value here is the same as the value of this semi-definite program. So what is it about? So we have two matrix variables S and T, and they basically, the multipliers for the constraint x transpose x minus I is 0, and the other multiplier is for x transpose minus identity is 0. So these are Lagrange multipliers. They are unconstrained because they are multipliers for equations, and it turns out that if you maximize the trace of these two multipliers under the condition that this Kronecker product term here is positive semi-definite, this is has the same value as this problem. This is not obvious, but it's not terribly difficult to see. Now in our case, if the matrix K is, if one of the matrices has size K, you have to change the formulation a little bit. So basically, what you get is x transpose x equals I. So this is now a k by k multiplier because x is n by k. So x transpose x is k by k. So one multiplier s is of order k, and the other one, if you look at x transpose, this is not going to be equal to the identity if x is only n by k, but it's semi-definite in the semi-definite sense. It's less than the identity. So in other words, x transpose is less than the identity in the Löwner order. And so this is a semi-definiteness condition, and this is why the second multiplier, the T, the n by n matrix, is a semi-definite matrix. But other than that, it's the same statement. So you have a Kronecker term here, and okay. So now let's apply this to our problem. So this was the general statement, we can write this quadratic form as a semi-definite program. So now let's apply it to our nasty thing here. So this is what we started out with. Then we went to so this is in X, this is in the orthogonal columns. So this is a complicated matrix, B tilde is a complicated matrix, but if we substitute everything properly, we get this semi-definite program. Okay, but now the Laplacian is depending on parameters. So now this L here depends on the weights. So this L is actually an L of X. X values on the weights. So, but we just substitute. So if we substitute, so everything is constant except L of X. So now we simply have additional linear variables, xij, which are greater or equal to 0, and their sum has to be something. So this shows that this concave problem, maximizing this function here, this concave problem is actually a semi-definite program, namely this one here. So it shows that in principle we have strong machinery to solve it, but of course if you go to big problems, you actually do not want to solve this semi-definite program. Because just these Kronecker terms, these are matrices for order nk by nk. So if n is already 10,000, and you want to, maybe you want to see 10 partition blocks, this is something you cannot even store. Okay, so that's too bad. So we do it. We maximize this function directly. I mean, I can evaluate the function. If you give me an x, I can evaluate all the eigenvalues, and moreover, I can compute subgradients. For eigenvalue functions, evaluating subgradients is not complicated. So basically, what I get is, you give me an x, I give you back the value of the function plus a subgradient direction. Now you just do the usual stuff, to use subgradient optimization to maximize this function. And of course, I'm modest. I want to. I'm happy if I can get the lower bound from negative to positive. That's all I'm interested in. Yes.
So, because the ways that you're interested in, there should be no negative and sum up to something.
Yes.
And sometimes, like usually the right notion of subgradient descent would be this multiplicative weight in this context, because it will automatically, it will step naturally in the syntax. So you don't have to project if you go.
Yeah. So I haven't looked at this. So
it would be like exactly the right setup for multiplicative weights.
I have to think about this. At the moment, I have to do projections on the simplex. Yes.
So, in this context, multiplicative weights is like subgradients, but it does the projections automatically.
Automatically, yes, yes. Thanks.
I've got a question as well. Well, not a question, but more of an observation, I suppose. I thought that in the early 90s, people like Polynomial and maybe you and Delorme and people,
yes,
they were originally using eigenvalue optimization because STP wasn't very well developed. And
he had no idea what STP was at that time.
Yeah, so in a way, this is almost like using an older method, isn't it? Or not?
It's, yes, I come back to the eigenvalue method, but I try to do something new with it.
Oh, right.
So this weight redistribution is something not completely obvious to do.
Right.
Let's see what comes next. Okay, so I come to the end more or less. So let's see what this does on some small toy examples. So here I did the following experiments just to make a sanity check. So I generated a random graph. So the density in here is 25%. So it looks very dense because the dots are very big, but it's only a quarter of the edges are there, and this is 0. So there are no edges here, and here's the separator. So it's what is the size here? Oh yeah, it's a graph on 200 nodes, and the blocks have size 90, so this should be size 20. And now let's see what do we get if we just look at the eigenvalues, at the lower bound given by the eigenvalues. And here's the picture. So I look at one of the columns of the resulting optimizer that I get back. So it should be, ideally, the optimizer should be a 0-1 vector. And so if you look at the blue curve here, this is the eigenvector if you set all the edge weights equal to 1 without any weight redistribution. So it pretty much captures that the first 90 nodes should have almost equal 1. The next 90 nodes, they should be orthogonal, they should be in the other set, and here the separator is just does funny things. Of course, it can go negative. I cannot control it. So this is what you get. So now you do a few iterations of weight redistribution, and then you look at the eigenvector, and then you get this red curve here. So it stabilizes really nicely. It stabilizes nicely, and also here, so all these bumps are all gone. So it shows that the method is not completely stupid.
And you mean several iterations? So you are solving your SDP in by iterations.
Oh no, so I don't solve the SDP. I compute eigenvalues, I compute subgradients, I move somewhere, and I stop when I get bored. I didn't say any details what I do precisely.
Okay, so it solves the SDP as well.
It solves this, yes.
So in some sense, yeah, you are doing this.
So of course this was a bit too easy because the separator was, oh yeah, so where are the big weights? So somehow this is something I do not really understand how to make use of it. So if you have a weight redistribution, some weights will become big and others will be very small. But I'm not really sure what I learned from this. But anyway, I thought it's nice to see where are the big weights. So here are the big weights. Okay, another example. So recognize this 5-block structure. It's constructed in a similar way. And again, so the original eigenvector without weight redistribution is a little bit erratic. So it's, yeah. And if you do some weight redistribution, it looks a bit nicer. And so now let's look at larger problems. So what is the general strategy? So first of all, I have to guess the sizes of the cardinalities. So if we agree that we want to partition into 3 blocks, so find a vertex separator that separates the graph into 2 pieces. Basically, what I'm guessing is the size of the separator, and I change and play with it. So first step, guess the sizes. Second step, do the hard work, do the eigenvalue optimization, and see what you get. And in the end, so eventually you extract the optimizer, which is a matrix, an n by k matrix, which has the right row sums, the right column sums. The columns are orthogonal, but they can be negative. So this is what we have. So now take this solution and do some rounding. Turn it into a 0-1 solution. How you do it, I don't know. Just try out things that work.
Can those weights not help you to do the rounding?
Yeah, this is what we are looking at. So at the moment, this is really work in progress. So specifying these steps and making them to work nicely is something we work on. So then you have a first feasible solution. So now you could say, well, this is one solution. First of all, let's try whether we can make it better. So do some local improvements. So then the number of edges is really small. Then you still have perhaps some edges in the cut. It's not guaranteed that we cut nothing. So then if you do a final cleanup to get rid of all the edges in the cut. And this is, so I don't want to explain how you do it, but this can be done. You just make the separator a little bit larger. So here are some results on some instances from this matrix collection. So here's the size of the matrix. So it goes from, so I think none of the sizes is smaller than 400, and this is the largest one with 900. And so the interesting thing is these 3 columns here. So VNS is simply one of the heuristics that people use to find vertex separators. I think it's called variable neighborhood search. So you start out somehow and try to improve and do something by local search. Now this is what we find if we use as a starting solution what we've got from our eigenvalue optimization. So you see, this really helps the local search. It's always, it's pretty much better. And this is best known, I think I'm a little bit vague here. This is best known, so we don't know whether these values are optimal or not. But it shows, it should give you a flavor in what range we are with our solution. So this is far from optimized. So this is just the first shot, and there's lots of room to fine-tune everything. And I think I'm more or less done. So this is a nice problem. I like the interplay between eigenvalue optimization, orthogonal relaxations, and semi-definite programming. This is really very, very nice. It's a very nice structure, and you can jump from one model to the other if it's useful, and go back and learn. And so this is nice. So of course I hope to deal with much larger graphs than 1,000 nodes. So my goal would be to beyond 10,000. So whenever the eigenvalue computation breaks down, then I would stop. Yeah, there's one theoretical paper out, and or not out. It's going to be out in probably this year. Fields Institute Communications. And I thank for your attention.
Thanks. Any questions or comment?
So, for me, it's not clear how to decide whether to stop. So you choose those vector m, and then you do your iterative algorithm. So you would be happy to stop whenever you get something which is larger than 0. But could be also that your initial set m is not.
Oh yes, absolutely. So you do this for several choices of the m's, of the cardinalities.
Yeah, but if for the given m is not existing in the separator, and then you cannot improve your bound because there is not existence, so you stay somewhere below the 0. So how is your?
No, so I can always, if I have an edge cut, so if I have few edges in the cut, I can always fix them by making the separator bigger, by increasing basically the mk. So this is something. So at the moment, I'm happy to have a more or less a concept that you can use. So this has to be worked with. Yes, absolutely. So who gives you good guesses for these problems? This was a question.
Sort of.
Well, I actually have a request.
Yes?
Well, maybe not for you, but for some other people in the audience. What about a tutorial on the multiplicative weights technique? I think it would be very nice to understand what exactly is going on in the text.
Absolutely.
Yeah. Is there a way to interpret that weight distribution? Is it some kind of Lagrangian relaxation in disguise, or? Because I've seen other optimization problems where they say, oh, you can play with these weights, but actually, if you look at it, what you're really doing is you're using an implicitly you're using some equation that these two quantities are equal, and that's why you can do that.
I don't think so, because I changed the nature of the problem. So if I change the weights, it means I measure the cut with respect to the weights. So not with respect to the original edges. So small weight in the changed problem could still mean a lot of edges in the original problem.
So when you looked at this sort of a result of your weights update, so could you look at the resulting graph and to try to see what kind of subgraphs you are picking up?
Yeah, this is something.
This is something. Thing to
yes,
try.
Yes, absolutely. But I have nothing to say in this. So this is still we do not understand ourselves what's going on.
Have you even looked at the resulting things? Like, do you pick up as a subgraph that is like maybe low diameter or maybe high diameter or whatever? No.
I understand your question, but I have no answer yet. Yes, David?
So when you change the weights, do you have to recompute the eigenvalues from scratch, or can you do it sort of in different methods?
I use an eigenvalue solver that actually can use starting points. But it's a bit tricky, so you have to make sure that the solver, so if you make very small changes, the solver says, oh, I've more or less almost the accurate eigenvalue anyway, so it doesn't do anything and says, okay, here are the old values. So you have to force the solver to do something.
So are you using a Lanczos?
Exactly, yes, absolutely. Lanczos plus Chebyshev acceleration I mean, full power from the numerical linear algebra. Yes?
You said you don't quite know how to round the x? Or
Yes, so this is something.
so there are, I mean, okay, so for these kind of things, they are sort of hybrids of this Cheeker style rounding and hyperplane rounding.
Yes.
And at least sort of theoretically they work.
I guess the problem is that even if you get a solution that's approximately okay, if you've just got one edge in the wrong place, it won't be a separator anymore. That's the problem. So which you don't get in
So
something
yeah,
like
you have to do some
Max
kind of cleanup, like this
Yeah.
local
Yes.
improvement, I mean, some kind of local improvement kind of things. But
So-
at least, so what this will guarantee you is that a small number, so with respect to the edge rates that you currently have, only a small number of edges will be cut after you do
Yes.
the rounding.
Yes.
And then, of course, you have to be, you hope to be lucky, and that means that you get so that's intrinsic in your approach, right? Because you model the vertex separators by saying, I want to reweight edges and then find just edge separators.
Yes, exactly. Of course, the bad case would occur if you look at a row of this optimizer and every entry is roughly 1/k. This is in principle possible.
So, I'm not sure. I mean, some of these things. I mean, like these random projection things. They can help to clean up some of these things.
So I would be interested to get some specific pointers, because at the moment we are just doing the completely naive thing. So just look at big numbers, but I'm sure there must be some more intelligent ways where you use global, where you somehow take global information from X to do the rounding.
Any other questions? Okay, that's thanks, speaker.